505. So let me define the theory first and then give you some motivation why we need it. Okay, so for this theory, yielding occurs when the distortion strain energy per unit volume reaches or exceeds the distortion energy per unit volume in simple tension or compression, depending on the kind of behavior you're studying. Experiment of the same material. Okay, so that's the keywords: distortion, strain, energy per unit volume. So we need to define this. So there is this somehow related to some energy, and I'll define that in a bit. Second piece is that it should exceed the distortion energy per unit volume in simple tension compression experiment. This is something we've seen in the past. It's a specimen which is subjected to tension or compression, and then you keep loading it till it fails. And so we're interested in computing the energy when it just fails, which I think we can compute given that we know the yield strength. Okay, and then the last piece which connects the two is reaches or exceeds. So it's just equating the things marked in blue should be greater than things marked in green, and then we have that theory. So let's try to first understand what distortion strain energy is. Once we've set that up, it's kind of easy to compute that formula, and then I'll also give you a motivation behind why we use this theory. So let's see what's distortion energy first. Okay, so let's consider a cuboid. It's subject to stress on all 6 sides. So sigma x, sigma y, tau xy, tau xz, tau yz. And once you have these 6 stresses, 3 normal, 3 shear stresses, you can compute the principal stresses. So those, but now you should be able to see the screen. Okay, everything is good. Okay, so what we can do is, if things are linear, then we can decompose this stress into 2 parts. An average stress, which I'll call sigma average. And then the part which is the subtraction of sigma 1 minus sigma average. So the same shape, same element, just that it's subjected to sigma 1 minus sigma average, sigma 2 minus sigma average, sigma 3 minus sigma average. So sigma average is just the mean of the stresses. Okay, so you can see that if you add the stresses on the right side, that is, you just take the component the x, y, z, then you will get the thing on the left because it's a superposition. That is, you can add the stresses to sum the stresses up. So this is a general stress equals, this is known as a hydrostatic stress. Okay, hydrostatic comes from the fact that if you have like a usual, let's say a balloon and you fill it with air, then all the forces on all sides will be, or the pressure on all sides will be constant, right? And that's hydrostatic. And this part is the distortion energy part. So under hydrostatic stress, you will not see a shape change. So if it starts as a cube, and then you keep, for example, it's a balloon, and then you keep blowing in air, you'll see that the shape of the balloon is basically the same. If it's, for example, if it's a sphere, it will keep remaining a sphere, but the radius will keep increasing, right? There is no distortion, or there is no shear, so to say. So the second part is the one which gives rise to a strain. It's the distortion part. That's because the stresses on all sides are not equal. So what we're saying here is that for this theory, it's the second part, the energy related to the second part, which is important. So we need to compute the distortion energy per unit volume from here, for that part. Now, why do we use this theory? It turns out that when they loaded specimens in, when they had specimens loaded with sigma average, and they kept increasing sigma average, they found that maximum shear stress theory is not able to explain the failure of those materials, indicating that there's something else going on. So then they tried to compute the distortion part. They found that the distortion part actually contributes to failure. So again, this is an empirical observation. Based on that, you make a hypothesis that this might be what's going on. Once you have a hypothesis, you do an experiment to see if what predictions come from the theory explain the experiment. If it does, then you say the theory holds true. And that's what is true here. So what we need to do now is develop a formula for the distortion energy. And then we all set, we know what to do with predicting failure with this theory. So in order to do that, what we'll do is we'll find the energy due to the first part, and we'll subtract that from the energy due to the hydrostatic part, and that's how we'll get the energy due to the distortion part. Okay, so let's do that. Okay, let's just call this, let's say, A, B, and C. So our goal is energy in C is energy equals energy in A minus energy in B. And that's how we get energy in C. So let's compute strain energy generic stress. Okay, this is the formula. The strain energy is U. And here it's really the U per unit volume because I'm using half strain in direction 1, principal stress in direction 1, stress 2, sigma 2, strain 3, sigma 3. Okay, but we have already seen the formula for strain energy 1. It's basically sigma 1 divided by E minus the Poisson's ratio divided by E sigma 2 plus sigma 3, and so on. So you can write a similar formula for strain energy in the second and third direction. So what you need to do is sub in the second expression, the first one, and you get this expression. 1 divided by 2E. This is Poisson's ratio. It's oh, this one? U. Sigma 1, sigma 2 plus sigma 2, sigma 3. Okay, next strain energy. Okay, so the case B, which is strain energy to hydrostatic stress, is a special case of the first case where sigma 1 equals sigma 2 equals sigma average, which is 1/3 sigma 1 plus sigma 2 plus sigma 3. So let's just call this 1 or I. Substitute in 1. And so we can just compute the formula for U. So let me just call that UA. Then we can subtract it conveniently. UA is this is going to be UB. Yeah, so you just need to substitute that value in 1, and then you get something like this: 3, 1 minus 2 nu divided by E sigma 1 plus sigma 2 plus sigma 3 divided by 3 squared. Okay, so we've got an expression for strain energy in both cases, A and B. So to find strain energy in part C, you just have to subtract UA from UB. So UA minus UB gives UC. Yes. 2 nu, Poisson's ratio. Nu, NU, and nu is Poisson's ratio. Comes later. Okay, so here is part C, strain energy due to distortion. So that's going to be UC equals UA minus UB. So I'm just going to write the final expression. It comes out to be 1 plus nu divided by E, 3E, then sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3. Okay, so that's it. That's the formula we were after. Okay, so once we have this formula, now so that's basically it gives us the part that's shown in blue. Right, we wanted to compute the energy due to distortion. That is what has been computed. Okay, so next is the failure criterion. So what we know that we want to predict the stress when the specimen fails in a simple tension or compression experiment, right? And then we also want to find the distortion energy. So now we've already done most of the work. We only need to compute what that formula or that energy would be in simple tension or compression, which is this loading, right? Uniaxial loading. So when you have uniaxial loading, we know that one of the stress would be the uniaxial. There's only one principal stress, and that's called as sigma 1. That will be Sy, because it fails when the stress is yield strength, or sorry, it becomes nonlinear when it reaches Sy, and that's we're just designing. We don't want it to go beyond the yield strength where things become nonlinear. And then sigma 2 equals sigma 3 equals 0. And so if you call this number 2, we just sub in 2. UC equals 1 plus mu divided by 3e. So we'll have Sy squared plus 0 plus minus Sy squared divided by 2. And so it comes out to be UC equals when to there mu divided by 3e Sy squared. Okay, so that was the part I showed in green in the theory, no, in the notes. And so we want to pretty much, if you want to predict failure in this theory, we just say that 2 should be greater than, let me call that 3. So when 2 exceeds 3, we have failure. So that comes out to be sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square divided by 2. Okay, so what I'm going to do is instead of keeping the square, I'm just going to take the square root. And so this would be a better way to root half. So raised to half equals Sy. And what I did here was I just took square roots of both sides. Right? I took this 2 and took the square root. I took this one and took the square root. So if you want, you can just is what I did. Okay, so I did that because this stress on the left side is called has a special name. It's will be denoted by sigma prime, and sigma prime is known as the von This is stress. So the theory states that the one misses stress, this should be, sorry, this should be greater than, right? This is part. So when the one misses stress exceeds the yield strength of the material, that's when we'll have failure. And that's what is predicted by the distortion energy theory. Okay, so again, compare this theory, which is this very complicated formula involving sigma 1, sigma 2, and sigma 3 with the case for maximum shear stress. Right, that's the tau max is greater than Sy divided by 2. That was the maximum shear stress theory. Okay, now let's see what that contour looks like for a 2D case. So this is what it looked for maximum shear stress. The area under the yellow is the safe region. If your stress is outside that region, it's failure. So we can do something similar for one misses stress. So for that, we're talking about a 2D case. So let's do the 2D case. So distortion, we call that DE for distortion energy. So this we abbreviate it here and then use that. For 2D. Okay, so for 2D, sigma 1, let's call that sigma A. Okay, but sigma A is clearly one of the principal stress found from the mode circle. Sigma 2 is sigma B. And then sigma 3 is 0. Plane stress will have one stress, 0. So if you put that in, let's call this formula 4. Substitute in 4, we have sigma prime equals sigma A minus sigma B square plus sigma A square plus sigma B square divided by 2 greater than Sy. And so I'm going to just simplify this. Sigma prime equals sigma A square plus sigma B square minus sigma A, sigma B, the whole raised to half is greater than Sy. Okay, so if we plot, just like we plotted before, the maximum shear stress theory in the principle on the sigma A, sigma B plane, where sigma A say on the x-axis, sigma B on the y-axis, then it follows this equation. Now for maximum shear stress, it was this thing which looked like a sort of like a hexagon. But do you know what that equation is? Left-hand side. If sigma A is x and sigma B is y, do you identify what that equation is? Okay, that's the equation of an ellipse. Okay, x squared plus y squared minus x times y. So the ellipse is actually not along the x or y axis, it's actually at 45 degrees to the x-axis because the factors before A, sigma A and sigma B is 1. And so it looks something like this. So sigma A, sigma B, It'll be something like this. Let me just redraw it. It's actually a better way to draw it is to first draw the distortion, the maximum shear stress theory. Let's just draw that first. So the maximum shear stress theory will be this line is incorrect. So 4 to so that's SY minus SY minus SY. And so we just have to join these lines they are at 45 degrees. Okay, so once we've drawn this, it's actually pretty easy to draw the ellipse. It passes through all the corners of this hexagon. So this is the P contour, and this one is the MSS contour, and this line is of course 45 degrees to the X and of course the Y axis. That equation is sigma A square plus sigma B square minus sigma A sigma B. So everything in yellow is the safe region for the maximum shear stress theory as well as the maximum distortion energy theory. Right. However, the part I'm going to show in, let's see, blue is also safe for distortion energy theory. Okay. And then the blue as well as the yellow safe for T. Okay, so looking at this figure, what we see is that the part in yellow is also enclosed by the part in blue, which means that the maximum shear stress theory is more conservative than the distortion energy theory. And the reason why is because it can So for example, if you look at this point, so the stress there, the part shown in blue, dark blue, that one is unsafe for the MSS, but safe for distortion energy theory, right? Safe for TE, not MSS. So the MSS says that the part will fail there, but D is saying it will not. And that's why MSS is more conservative of the two. So MSS is more conservative than T. Okay, sometimes you want to design using MSS because you want to keep the designs more safe. Well, sometimes you care too much about, so safer designs tend to have a higher factor of safety. Higher factor of safety means things are thicker, more diameter, more material, they tend to become heavier. And so something which probably sits on the floor and not moving, like civil structures, you probably want to make them very safe. And so you'll use the more conservative theory. On the other hand, when you design things which move, where you're burning fuel to make them move, like planes or cars, you want to keep the material as light as possible, which means the factor of safety is lower relative to something which is not moving. And that's where you probably want to use a theory like distortion energy theory to build it. Now, there are points where both of them agree completely, right? This, for example, this point, this point, this point. The 6 corners are the corners where things are the same, predictions are the same. For other places, they are not. So it's just a matter of judgment which theory you will use to design the part or element. Okay, so how do you do design? It's the same principle as before. You take the factor of safety and then use that to compute the allowable stress. So design using TE. We use the factor of safety or design factor depending on which side of the spectrum you are. So ND or N equals SY divided by sigma prime, where sigma prime is, of course, the one misses stress. One misses sigma X, sigma Y, XY. So we've looked at the formula for one misses based on sigma 1, sigma 2, and sigma 3. If you want to compute the one misses stress in terms of the principal stresses, sigma Y, sigma X, and tau XY, like in typical problem, you won't be given the principal stresses, then you can use this formula which transforms stress from principal stresses to sigma X, sigma Y to compute the required expression, so plus or minus sigma X minus sigma Y plus tau XY squared. So this is an expression for sigma prime in terms of sigma X and sigma Y and tau XY. And the power raised to half. Now you could also, now I've only talked about using distortion energy for simple tension and compression experiments. You could also use this for shear. This is how you can use it for shear. So using D for shear. For shear. Okay, so for shear, that's what's the last formula number I wrote? 4, okay, 5. Let's call this 5. But sigma x equals sigma y equals 0, right? And the shear, the normal stress is 0. And so we have sigma prime equals I made a mistake here. My bad. There should be a 3 there. And also it should be, it's dimensionally inconsistent. This has to be square and this has to be 3 there, right? The 3 was not, but the square, without the square doesn't make sense. Otherwise, dimensionally inconsistent. So please add the 3 times 3 and then the square. So if you put sigma x equals sigma y equals 0, then we have tau x y. The whole thing raised to half is equal to sy, right? Because the condition is sigma prime should be greater than equal to. If you want greater than equal to, it's also good enough. And so then tau xy is greater than, so you have to take the square root of 3 and take 1 over square root over 3, so 0.577 is. So this is the expression for shear stress. If you have only shear stress in the element, then you will use not yield strength, but you'd use 0.577 yield strength to design for the element for shear. So that will give you tau xy. Once you get tau xy, you will go and compute tau xy using the shear, the simple formula we had, that VQ divided by IB. And from that, you can design for the geometry based on that question. Okay, so let's try to apply all this, what we have done for von Mises and shear and maximum shear stress onto a problem. I'm going to do a problem, and that should be it. So 40, 80 MPa. And then the maximum, the shear stress is 25 MPa. Okay, so that's our stress element. So assume, oh yeah, good catch. It should be always, yeah. Otherwise it will start moving, right? 25 MPa. 80 MPa. This is 80 and 40. Yeah, my bad. 40 M. So assume SY equals 250 MPa. Okay. Compute the factor of safety assuming A yield due to Mises Yes, so we are assuming that that particular loading condition leads to yielding essentially. and we are given the yield strength, Sy. So we need to figure out what the factor of safety is. Okay, so let's recap the formulas we need to use for dE. The formula is sigma 1 square plus sigma 2 square minus sigma 1 sigma 3 maybe I've written it slightly differently here just to make it consistent. Yeah, so for plane stress, I wrote it this way. Let me write it in terms of sigma A and sigma B, where sigma A and sigma B are the principal stresses. So let's be consistent. So sigma A square plus sigma B square minus sigma A sigma B half is the this is the bond versus stress. And then for MSS, we need tau max, which is sigma 1 minus sigma 3 divided by 2 is the maximum shear stress, right? So I'll come to that. Let me just write down the formulas and then we'll show you what A and B is. So we've got this. And then the factor of safety is the yield strength divided by sigma prime. Let me just write in the same line. So N for this is Sy divided by sigma prime. And for this it is Sy divided by 2 by tau max. Right? So we've set up all the equations. Now it's just a matter of figuring out those values, right? Sigma y, Sy is given. Sigma prime comes from this formula. We just have to get that. Tau max comes from this formula. So we only need to compute those two values, sigma prime and tau max, and we're done, right? So let's see what those are. So here the stresses are in terms of principal stresses. Okay, sigma A and sigma B are the principal stresses. They are sigma A, sigma B. And so since I'm out of time, and since you already know how to compute the principal stresses, I'll skip that. You could use number A, Mohr circle, or you can use the principal stress equation transformations to figure out sigma A and sigma B. So using either Mohr's or stress transformation formula, we have sigma A equals -85, sigma B equals -45. Okay, so that pretty much gives us sigma prime because it's only a function of sigma and sigma B. Now for the maximum shear stress theory, we need tau max, right? So for that, what we need to do is we need to rearrange these in descending order. So the third stress is 0, right? Because it's a plane stress condition. So then sigma 1 is greater than sigma 2 is greater than sigma 3. And we just look at that and see that sigma 1, the max stress is sigma A. Sigma 2 is in this case sigma C, because the third stress is compressive. So sigma 1 is 85, sigma 3 is -45. So now if you see these equations, we have computed, or we have values for all these things, just a matter of substituting back in that formula. Let's call this 1. This is 2. So I'm just going to write down the final answer because I pretty much filled the dots to what we need. So substituting 2 in 1 and using sy equals to 50, we have n distortion energy comes out to be 2.18. And n MSS is 1.92. Okay, and you can see that this theory is more conservative. Okay, lower n. Okay, so the lower the n is, the more conservative.